Hi everyone, today our topic is about real numbers. So if you recall, every rational number can be rewritten as a decimal by dividing by the numerator by the denominator. So in other words, it makes a ratio or a fraction. All right, let's take a look at the first example from the book, example 20. So we need to express 3/8 as a decimal. So remember, when changing a fraction into a decimal, all you have to do is take that top number, 3, the numerator, and divide it by your denominator, 8. So to set it up with long division, you would put the first number inside and the second number outside because that's the one you're dividing into. Okay, so it's not always the small numbers on the outside. It's the first number that's on the inside. Okay, so 8 doesn't go into 3, so we'll put a 0 there. And we'll add a 0 in the back of 3 after the decimal point. 8 goes into 30 3 times. So that gives us a remainder of 6. Add in another 0, bring it down. 8 goes into 6 7 times. 8 times 7 is 56. Subtract that, we get a remainder of 4. Add another 0, bring that down. 8 goes into 40 5 times for a remainder of 0. So that's how we know we're done. So the answer as a decimal is 0.375 or 375 thousandths because it's tenths, hundredths, thousandths. So 375 thousandths. Okay, if I needed to use my calculator, again, I would take the first number, the numerator, divided by my second number, the denominator. And I would also get 0.375 or 375 thousandths. Now, is this a repeating or terminating decimal? This is a terminating decimal, meaning that it ends. It doesn't go on forever. It just, after the decimal point, it's 3, 7, and then 5, and then it's done, okay? We also say that it is finite. So it's kind of like the opposite of infinite, right? Infinite means it goes on forever. This doesn't go on forever, so we call it a finite decimal. Okay, so you can either have a repeating decimal or a terminating decimal. This one is an example of a terminating decimal because it ends. It ends at 5 and it doesn't go on forever. Let's take a look now at another example. Here we have express 9/11ths as a decimal. Go ahead and pause the video and try that on your own first. Okay, so 2 ways you can think about it. You can take your numerator, 9, and divide by your denominator, 9 divided by 11. And then in your long division, remember the first number goes inside. It's being divided by 11 to see how many times 11 goes into 9. 11 can't go into 9, so we're going to add a decimal point and a 0 in the back so it doesn't change the value of 9. It's just 9 and 0 tenths. Now 11 goes into 90, let's see, 8 times for 88. That gives us a remainder of 2. Add another 0 and it becomes 20. 11 goes into 20 11 times. Gives us a remainder of 9. Give it another 0. 11 goes into 90 8 times. We already did that up here. And we chose 8, right? 8 times 11 was 88. We got a remainder of 2. We're going to get it again. Bring down another 0. We get a 20. We did that up here. We chose 1. So we have 20 minus 1. which is, sorry, 11, which is 9, and you start to see what's going on, right? It just keeps repeating, repeating, repeating. So we can assume that it's just going to be 8, 1, 8, 1, 8, 1, and going on and on and on in that pattern. Okay? We can also check it with our calculator. 9 divided by 11 is indeed going to be 0.8181818181, and so on. Okay? In the calculator, it shows that it ends at 8, but in actuality, it goes on forever. Your calculator just can't possibly show all the repeating decimals, right? So it's going to cut it off at some point. So don't be fooled by your calculator, because your calculator literally can't show you that it goes on forever. So how do we write this decimal showing that it goes on forever in that pattern? Well, we know that the 8 and the 1 are the ones that are repeating, so we put a bar over the 8 and the 1 to show that it is repeating. Now keep in mind, if I were to put a bar over just the 1, then that would actually mean that just the 1 is repeating and going on forever. Okay, so that's why it's important for you to put the bar above 8 and 1 to show that it's a pattern of 8, 1, 8, 1, 8, 1, and so on. Okay, so it's not this one. And, you know, we already said it multiple times, but this is a repeating decimal. Repeating because it goes in a pattern. Okay, so it's repeating. It's going in a pattern. And it is not finite. It does go on and on and on forever. Okay? So you're probably thinking to yourself now, why are some decimals like that? Why are some fractions going to give us a terminating decimal? And why are some going to be repeating? Let's take a closer look at some of the numbers. So here's an example. We have negative 1/2, we have a third, we have 5/6, we have negative 4/9, we have negative 8/11, we have 1/7, negative 3/14, and 9/25. So a bunch of different fractions with different denominators. We're going to explore all their decimal forms. And we're going to cheat a little. We're going to use the calculator, or else this is going to take us forever. So for the first one, negative 1/2. I'm going to take 1 and divide it by 2. You should probably already know what that answer is. It's 0.5. Okay? And it's a negative, so it's going to equal to negative 0.5. We don't really care about the negative. We really care about the decimal part, but just know that this is a negative number. So we do have to keep that negative. All right, next one is 1/3. So we're going to take 1 and divide it by 3. I get a repeating decimal. Remember, just because you see an end in your calculator doesn't mean that the number actually ends. It's repeating. Okay, so we're going to write it as 0.3 or 3/10 with a bar over the 3 to show that the 3 is repeating on and on and on. All right, 5/6. 5 divided by 6. I get 0.833333333. That 3 is repeating. Remember, it goes on forever. Your calculator just can't show that. So I'm going to write 0.83 with the bar over just the 3, because only the 3 is being repeated here. All right, next number, 4/9. 4 divided by 9. That is a repeating decimal as well. The 4 is repeating. So 0.4 with the bar over just the 4. All right, next one, 8/11. Negative 8/11. 8 divided by 11. And we get 0.72727272. So let's write that down. The 7 and 2 were both repeating together in that pattern, so we're going to put the bar over both of them. All right, next one, 1/7. 1 divided by 7. I get this, 0.14285. 14285. 7. Okay, so it looks like 1, 4, 2, 8, 5, 7 is what's repeating. Wow, that's a lot of numbers to be repeating. 1, 4, 2, 8, 5, 7. Okay, so 0.1, 4, 2, 8, 5, 7. All of that is repeating. Wow. Now, if you notice, it says 1, 4, 2, 8, 5, 7, 1, 4, 2, 8, 5, 7, and then it says 1, 4, 3. So that looks like it's terminating, that it has an end, but it doesn't. The reason why we have a 3 at the end is because it's 1, 4, 2, 8, 5, 7. We're taking the 8, which is 5 or greater, and they're rounding it up to a 3. So instead of 1, 4, 2 at the end getting cut off, they rounded because the 8, the next decimal place, is 5 or greater, so it rounds that 2 up to a 3. So your calculator is trying to be as accurate as possible when estimating because it does go on forever. All right, next number, -3/14. 3 divided by 14. What do we get? 0.214285 142857. Okay, so I don't see the 2 repeating anymore. Let's see, 142857, 142857, and then we go 142857. So there's a 2 in the front that doesn't repeat. -2, 142857. Did I get all that? That was a lot repeating. 2, 142857. Yeah, 142857. Wow, so remember that 2 wasn't repeating, just all the rest there. So that's a lot of repeating digits. All right, last one. 9/25. 9 divided by 25. I get 0.36. Whew, thanks. I needed a terminating decimal. Okay, so now let's try and categorize them. Which are terminating decimals? Ones that end and don't have a pattern. Okay, A, so that's -1/2. What else? And H. 9/25. And the ones that are repeating, all right, we have 1/3. We have 5/6. We have -4/9, -8/11, 1/7, -3/14. Oops. 3/14, and 9/25. Okay. So what do we notice? Well, it looks like we might have particular denominators that tend to always give us repeating decimals. Let's see. How about instead of 1/3, I try 2/3. 2 divided by 3. Yes, I also get a repeating decimal. Okay, what about with a 6 as a denominator? Let's try, I don't know, 1/6. Oh yes, definitely also repeating. Except for the 1, the 6 is repeating. Okay, what about something with a 9 on the bottom? Let's do 8/9. 8 divided by 9. Oh yes, also repeating. So it looks like the denominators might be our giveaway here. Okay, instead of 8/11s, let's do 5/11s. 0.45454545. Just like how 8/11s was 727272, right? So there's kind of a pattern there. For our 9 as a denominator, we got 4 repeating. And then if we do 8 divided by 9, we get 8 repeating. So it's the number, the numerator, that's repeating. So there's certain kind of patterns going on with your denominator. 1/7, let's do 4/7. Yep, also repeating. Let's do something with a 14 on the bottom. 13/14. How about that? 9, 2, 8, 5, 7, 1, 4, 2, 8, 5, 7, 1, 4, 2. Yeah. And, oh wait, we wrote 9/25ths, 25ths twice. So let's get rid of that one. That one is not repeating. Okay, so like I said, it seems like certain decimals will be repeating if they have certain denominators. So good to know. 3, 6, 9, 11, 7, and 14 will give us those repeating decimals. All right, so let's talk about these numbers then. So we have overarching the label real numbers. All these numbers, whether they're repeating or not, or terminating or not, are all called real numbers, okay? All the numbers you learned so far are real numbers. Then we can actually categorize them into two different types of real numbers. So rational numbers are what we call the terminating or repeating decimals. They're numbers that when changed into a decimal, they either end, they're terminating, or they repeat in a pattern, okay? So even if it's repeating, like -1/7 or 3/8, it has to repeat in a pattern. We call those rational numbers. And keep in mind that square root of 4, perfect squares, like square root of 9, those are also rational numbers because they can be reduced to, a whole number. Okay? So just because they have a square root doesn't mean that they're a special number. They still equal a whole number. Okay, now the other type of number is called an irrational number. So it's the opposite of the rational number. It's an irrational number. Now they have to repeat, they can't end, non-terminating, and they don't repeat. There's no pattern. So let's take a look at some of the examples. We like to use our square roots as examples because they're all over the place. Unless they're a perfect square, like square root of 4, square root of 9, square root of 81, which is 8, they actually don't have a pattern. So let's take a look at those two examples. Square root of 2. It's this mess. 1.414213562373095 and goes on forever with no pattern at all, no repeating, nothing. Okay, we call those irrational numbers. They're unpredictable. We have no idea what's going to happen with them. They're acting without any rationality at all. There's no way to see what's going to happen. Here's another example, square root of 3. Also, no pattern whatsoever. Okay, so either it ends or it has a pattern, we call it rational, or it doesn't end and it doesn't have a pattern, we call those irrational. Okay, now looking at our rational numbers, the ones that end or repeat, they can either be categorized as integers, so those are positive or negative whole numbers, or fractions. So either they're a whole number, they got no other remainders or any other parts, no decimals, or they do have some parts. They don't quite make a whole. And then with our integers, they're either positive and 0, or they're on the left side of the number line, they're negatives. Okay? So you're going to want to put this into your notebook just so you can have the vocabulary available when we're talking about real numbers versus rational, irrational, integers, fractions. And then I would be sure to also jot down these examples too, so that you have examples of numbers that fit each type of vocabulary word.